Hey everyone, today we're going to be taking a look at vectors and motion in 2D, in particular projectile motion. Here on the left we have a picture of Galileo Galilei. He was alive in the mid-1500s to mid-1600s, so he comes before Isaac Newton, so we study what he did before we study Newton's laws. And one of the things that he did was take a look at projectile motion. Now, Galileo is often called the father of modern science, or the father of the scientific method, even the father of modern physics. And so he's a pretty important figure in history. You may remember he's the guy who dropped the lead balls off the Leaning Tower of Pisa. So let's get into it. So what are vectors? Well, vectors point from one location to another location. They describe things which have direction, and they can be added and subtracted graphically or by components. We'll mostly be using their components, and we'll see when we get to projectile motion why we want to use their components. As an example here, we have a baseball, which is a velocity in black there, the v, but we can break v down into Vx and Vy. Vx here shown in blue and Vy shown in red. Now, knowing v and the angle theta, which is measured from the positive x-axis to the vector v, we can calculate Vx and Vy using sine and cosine. The x component is given by the magnitude of the vector v times the cosine of theta, and the y component is given as the magnitude of the vector v times the sine of the angle theta. So we want to make sure that theta is measured counterclockwise from the x-axis. If it's not, what ends up happening is the x component might end up being the sine of the angle you're given, and the y component might end up being the cosine of the angle that you're given. But as long as you make sure that theta is measured counterclockwise from the x-axis, the x component will always be with the cosine, and the y component will always be with the sine. So here's a couple other useful formulas from trigonometry. Again, we have a similar situation here with a vector being broken down into its x and y components. And using the definition of the tangent of an angle, opposite over adjacent, we can see that the tangent of theta here is given by the ratio of the y component to the x component. In other words, Vy divided by Vx. Well, whenever we break vectors into components like this, we always have this right triangle here in which we can apply the Pythagorean theorem, which we have as the second formula here. So the magnitude of the vector v squared is equal to the x component squared plus the y component squared, simply read from the triangle there. Often we'll want to take a square root of this formula on both sides, and we'll have the magnitude of the vector v. It's important to remember that components are just numbers, but vectors are vectors, right? So we can add vectors graphically, as we can see here from the vector v1 plus v2, giving us this resultant vector v sub r. But it's actually nice to just break down the vectors v1 and v2. Here we have v1x and v1y for v1, and here we have v2x and v2y. And we can see that if we add up each of the components, for example the two x components, we get vrx. And if we add up the two y components, v1y and v2y, we get vry. And so we can also break down that resultant vector into its components. And because all these vectors can be broken down into components, it's very nice because we can just work with x and just work with y. In the end, we can sum everything back together and form the full vectors. Okay, so solving problems with vectors, one of the things we always want to do is kind of what I just said. Always break them down into x and y components. Well then, once you've done that, write down formulas involving just x and just y components separately. That way you've isolated everything with x and everything with y. It makes solving problems, especially in physics, much easier. To calculate the magnitude of the vector you're interested in, just use that formula with the Pythagorean theorem. If you want to calculate the angle, you use this formula here, where we've taken the inverse tangent on both sides, so that the angle theta is the inverse tangent of Vy over Vx. Now, if you use this formula for the angle, that theta will always be measured from the positive x-axis to the vector, okay? So don't need to worry about where that angle is for this formula. Here we have two projectiles. One projectile is released from rest, while another projectile is simultaneously flicked in the x direction, so that it has an initial x component to its velocity. What we see as we compare the falling process of these two projectiles is that at every time interval, the projectiles fall the same distance in the y direction. That's because the projectiles both experience the same acceleration in the y direction, namely the gravitational acceleration. And neither of these projectiles were given an initial y component of velocity. However, one of them was given an x initial component for its velocity. And the x component of the velocity does not affect the vertical motion of the projectile. Since there is no acceleration in the x direction, we can see that the x component of the velocity never changes. Let's take a look at an example of projectile motion in 2 dimensions. This is a very general problem here where we're not given anything. I want to use this example to derive some useful formulas that will help you solve problems. Let's read the example now. A projectile is launched with an initial velocity at an angle theta. A. How high will the projectile travel? B. How long will the projectile be in the air? And C. How far will the projectile travel? Let's begin with part A. How high will the projectile travel? The projectile will move in the y direction as long as its y component of velocity is not 0. Well, therefore, the highest point must be when the velocity becomes 0 at its highest point, namely the y component of the velocity becomes 0. Because then the projectile will begin to fall. As a projectile rises, its velocity in the y direction will get smaller and smaller until it reaches 0, and then the projectile will begin to fall back towards the ground. So we know that the initial y position is something we can set to 0 because we choose our coordinate system. And we know that the y component of the acceleration is minus g, or minus 9.8 meters per second squared. We won't use numbers in this example though. So let's begin working on part A here. What we want to do is solve for when the y velocity is 0. Okay? But we're solving for t because we need a time that this projectile travels to reach its maximum height, and then we can use that time to calculate when the projectile reaches its max height, what that max height actually is. So we'll solve the above equation for t using the fact that the y component of the velocity should be 0 at the maximum height, and the y component of the acceleration is minus g. What we end up with here when we plug in these quantities is that the time it takes to get to max height is the initial y component of the velocity divided by g. go ahead and try this for yourself. Plug in those values and rearrange the equation for t, and make sure that you're getting the same answer that we have here. Now, in order to get the height, we use the y displacement equation for constant acceleration. Namely, this formula here. The final y position that we're interested in is equal to the initial y position plus the initial y velocity times the time plus 1/2 the y component of the acceleration times the time squared. Now we're going to plug in that time that we got before, but first let's go ahead and simplify this expression. We know that y0 is 0, and so we can get rid of one term, and we can replace ay with minus g, hence the minus sign in this final expression. So we'll take this expression and we'll use it to find the max height. What we want to do then is plug in for t now. So I've put t in parentheses here. So y final equals the initial y velocity times v0y divided by g, that's the time it takes to get to max height, minus 1/2 g times the time it takes to get to max height again, v0y divided by g, but we got to square that quantity. Okay, so don't forget to square both the top and the bottom. We can simplify this expression by combining some of the terms here. We see in the first term we have v0y squared over g, and in the second term, the only simplification we can do is cancel one of the g's. We have a g in the numerator and we have g squared in the denominator. That leaves us with 1g in the denominator. So finally, what we see here is we have 1 of something minus 1/2 of something. Notice those two somethings there are the same, v0y squared over g. So 1 minus 1/2 gives us 1/2 of that something, so we have 1/2 v0y squared divided by g, and it's positive, right? Because 1 minus 1/2 is positive 1/2. Okay, so try this for yourself. Go through that process there of plugging in the time it takes to get to the maximum height into our y displacement equation with the appropriate initial conditions. Plug in for the acceleration, and you should get this answer for yourself. Let's take a look at a couple notes here for part A. Some important things to note. The maximum height depends only on the y components of the velocity and acceleration. Again, the x components and y components shouldn't mesh together. However, we'll see later how the y components actually do affect the x component for projectile motion. If we launch the projectile off a cliff, we would simply add the height of the cliff to your final answer, okay? Because we begin at a higher initial point, well then our maximum height would be higher, right? And if a projectile is shot downward, do not use this formula. The maximum height would just be the initial position of the projectile, right? If the projectile begins at a certain position and is fired downward, well then the maximum height that that projectile was ever at was its initial position. Now we're ready to get into part B here. How long will the projectile be in the air? And we'll see a nice little relationship between this time and the time that we calculated previously. Although in general, there will be no relationship between those two times, or no simple relationship. We know that the projectile will be airborne until it returns to its initial position, right? Because we're launching a projectile from the ground, and we've set up our problem so that that projectile lands back on the ground at the same height. For us, what that means is that y final is also equal to 0, the same as y initial. So what we want to do is we want to solve that y displacement equation again. We're going to solve for a new time, but we're going to plug in our initial and final condition. That is that y0 and y final are equal to 0. So we're solving for t, and we're using these facts here, that y final equals 0 and y initial equals 0. What we ultimately end up with here is this expression, where I've gone ahead and factored out 1 power of t. So you go ahead and plug in y final and y initial, and then factor out a t and make sure that you get this result. Since we do have a t squared in our equation, in principle from our algebra rules, right, we have 2 solutions, and you can see that from this expression here. But let's go ahead and go to a new slide. So we have 2 solutions for this expression. When the term in parentheses is 0, that would be one solution, and when t equals 0, that would be our trivial solution. So t equals 0 corresponds to the projectile's starting location, so we're not interested in that. Therefore, the second solution must correspond to when the projectile has landed back on the ground after its complete travel time. Okay? So twice the time it takes to get to max height. If you remember, the time it takes to get to max height was the initial y velocity divided by g, and here we have twice the initial y velocity divided by g. So let's take a look at some notes here. So our notes for part B are that the total time of flight for projectile will be different if the projectile lands higher or lower than its initial position, and there will not be a simple relationship between it and the time it takes to get to maximum height. For example, if the projectile lands higher than its initial position, then the time it takes to land will be less. If the projectile lands lower than its initial position, well then it will take longer for that projectile to land. If the projectile returns to the same height, the time to get to maximum height will always be half the total time of flight. To put it another way, the total time of flight will always be twice the maximum height if the projectile begins and lands at the same height. Now we're ready to tackle part C here. How far will the projectile travel? Well, the projectile will move in the x direction as long as it's still in the air. Therefore, the farthest point must be when the projectile returns to ground level. This is called the range of the projectile. The fact that the furthest point must be when the projectile returns to ground level tells us that this range will depend on the initial y velocity. I'll let you think about why that's the case. Remember that the x component of the acceleration is always going to be 0 for projectile motion in our class. In order to get the range, we use the x displacement equation. Looks a lot like the y displacement equation, right? However, in this case, we always want to simplify first, right? And what we find when we simplify is a nice, neat little equation here, where almost all the terms are 0. Well, let's think about that. The initial x position is 0, because we get to choose the origin of our coordinate system. So we made y0 equal to 0, we can make x0 equal to 0 as well. And the x component of the acceleration must be 0, because this is projectile motion, and so we only have the gravitational acceleration in the y direction. Now what we need to do is plug in for t. Remember, we computed the time of flight in the previous part. Well, now we simply plug in that time of flight into our x equation. This is simple enough because our x equation is simple. And so for our final answer, just reorganizing these terms here, what we see is that the final x position is twice the x initial velocity times the y initial velocity divided by g. So here we see mixing of both x and y components of the velocity. Again, I'll let you think about why that's the case. Now this formula is a good formula here for us, and we should use this formula when we know the x and y components of the velocity and we begin and end at the same height. However, we may want to put this formula in a different alternate form using the trigonometry that the x component is equal to the magnitude times the cosine of the angle, and that the y component here is equal to the magnitude times the sine of the angle. Now, why would we want to do this? Well, it gets rid of the x and y components and replaces them with the magnitude of the velocity and the launch angle theta. Let's take a look at how it works here. So if I plug in for v0x and v0y, this is the expression that I have. So we have 2v0 cosine theta times v0 sine theta over g. In order to simplify this formula, it does look more complicated, but we can simplify it using some trigonometry, namely the double angle formula for sine. Sine of 2 theta equals 2 sine theta cosine theta. We get the following alternate form called the range formula. We call it the range formula, and we use capital R, meaning range. That v0 squared times sine of 2 theta divided by g is the range of the projectile. Again, remember that this formula only applies when we begin and end at the same height. Alright, let's recap before we end the video here with some notes for part C, and then a complete review of the problem and the formulas involved, and then we'll end the video. So, notes for part C. The range of the projectile will be different if it lands higher or lower than its initial position. Okay, if the projectile lands higher, then it will have less range. If the projectile lands lower, it will have more range. Both formulas work. It just depends on what kind of problem you're solving. Do you know the x and y components, or do you just know the initial velocity and the launch angle theta? Use whichever is more convenient for your particular problem. Finally, let's review the formulas that we derived. The time that it took to get to maximum height, we calculated, was the y component of the initial velocity divided by the gravitational acceleration g. It's a pretty simple formula. We took that time and we plugged it into our y displacement formula to get the maximum height. And the maximum height we found was v0y squared divided by 2g. So slightly more complicated formula. You need to remember the square there, and you need to remember the 2 in the denominator. And next we calculated the time of flight. We saw that the time of flight there, for our particular problem, where we begin and end at the same height, is given by twice the maximum height, or 2 times the y component of the initial velocity divided by g. And then finally here, we calculated the range of that projectile, and we saw that we could use the formula 2 times the x component times the y component divided by g, or we could use some trig and rewrite this as the range formula. In the common form that you see this formula is the initial velocity squared times the sine of twice the launch angle divided by g. Okay, so I hope that helps, and I'll see you guys next time.